Hello, everybody. My name is Masood Olia, and I'm a professor in the School of Engineering at Wentworth Institute of Technology. And I'm glad to be back with another problem related to dynamics, kinetics of particles. So here I have an example where they have this pulley system. As you could see, we have two blocks, A and B. The weight of A is 100 pounds. And the weight of B is 50 pounds. And A is moving down the incline with a velocity of 5 feet per second. And you could see the slope actually with a triangle of 3, 4, 5. So it's moving at 5 feet per second. And there is friction between this block A and the surface, mu k, coefficient of kinetic friction is given to be 0.2. So moving down at 5 feet per second, first of all, we want to find acceleration of block A, the 100-pound block. And then we also want to find the distance after we find the acceleration, find the distance block A will travel before it comes to rest. So because of friction, we are assuming that, well, as we solve the problem, we'll see that actually it's going to decelerate. So it will eventually come to rest. In other words, the friction is going to overcome the weight, so it's going to decelerate. So this is an interesting problem because besides the fact that we have to draw free body diagrams, and obviously the method we're going to use is going to be second law, F equal ma, because we want to find acceleration. And so it has kinetics free body diagrams, F equal ma. And then we have to also worry about the relation between acceleration of these blocks, which requires us to do some kinematics work. So let's start with the free body diagram of A. So I'm going to go ahead and draw the free body diagram of A here for you. Clearly, we're going to call these the x-axis. In fact, I'm going to call this guy a positive x-axis to be downward, because we know that this guy is moving, in fact, downward. And that's going to be my positive x-axis. And this is the y-axis. I'm going to put right here. So what forces are acting here? So be careful, there are two cables here. This is one cable here and one cable here. So I'm going to call the tension in the cable attached to block A, I'm going to call that tension A. So this is obviously an unknown. So that's tension A. The weight of the object is known. So I'm going to go back to black, things that are known. So that's the 100 pound, right? And we have a normal force. Let me go back to red. Clearly a normal force here in that direction. And then because this guy is moving down, so friction would be in this direction. So I call it F sub F being friction. Now, we know that in order to find friction force, we need to find N. So let's apply the equation of motion first in the Y direction, because there's nothing is happening in the Y direction, right? If you say sum of the forces in the Y equal MAY, there's no acceleration in the Y direction because the acceleration is this way. So this is our positive Y clearly. Now, before I do that, actually, let me come over here. If I call this angle theta, right? You see how based on that triangle, cosine theta becomes adjacent over hypotenuse 4/5, and sine theta becomes 3/5. So we don't have to know the angle really. We just need the sine and cosine. Okay, back here. So what do we have? N going in the positive direction. How much of this weight is in the Y direction? Clearly, this guy, this component, which is 100 cosine theta. So looks like I have to keep going back to black. So 100 cosine theta. And then remember, there's nothing on the right-hand side. There's no acceleration. So cosine theta, remember, is 4/5. So N becomes 80 pounds. Now, if you have N, then friction force, as we know, is mu K times N. So 0.2, that's given, 80 pounds for N. That's 16 pounds. So this friction force is 16 pounds here. All right, next, what do we do next? Well, let's apply the equation of motion in the X direction. So I'll do it right here for you, okay? Remember, I'm gonna call this positive direction because that's the direction of acceleration, or at least that's the way it's moving down. So be careful now. TA is gonna be negative, friction is gonna be negative. I'm gonna plug in the friction, 16 pounds a minute. don't forget, this is a typical mistake, guys. Don't forget that this 100 also has a component in that direction. Since 100 cosine theta was used for in the y direction, in the x direction, that guy is going to be 100 sine theta, which is 3/5, as you could see up here. That's the sine theta, equal mass. Now, another typical mistake, guys, is the weight of the object is 100 pounds. The mass is 100 over 32.2. You got to change it to slugs. So if you put the 16 here, and this is 3/5, and then clean it up, maybe we can multiply by negative, so TA becomes positive. And then looks like based on my calculation here, TA plus 44, that's the difference between the 16 and 60 after you multiply by negative, and then we have a minus 100 over 32.2. It's about 3.1056 roughly acceleration of A. So hold on to this equation. Right now we have two unknowns, tension of A and acceleration of A. Okay, what about B? Let's go and draw a free body diagram for B. We'll do that. B should be easy. So this is B. Now remember, I got it. This is a different tension in this cable. So I got to move this up a little bit, guys. So we have tension B here. Has nothing to do with this 16, by the way. Let me just remove this 16. That was the friction force that I used earlier for you. And the weight of B, which is 50 pounds. And then let's apply the equation of motion. Sum of the forces in Y equal MAY. Obviously, this guy is accelerating. So what do we have? We have tension B minus 50 pounds. Again, be careful. Mass of B is 50 over 32.2, right? Times the acceleration of B. Look, now we introduce two more unknowns. Tension B is different than tension A. Acceleration of B and acceleration of A are related, but we don't know that relation yet. That's why I said we have to do kinematics, dependent motion. All right, so what's next? The next thing, let's see if we can establish a relation between tension A and tension B. So we reduce the number of unknowns. Look at the free body diagram of Pulley. By the way, I should have mentioned that we are neglecting the weight of these pulleys here, pulley at C and pulley at D. Okay, so this is pulley C. This was the tension A. Remember, the same tension, one cable. And guess what? This is pulley D here. And then we have what? Tension B here. So because these pulleys don't have mass, if you say F equal MA, basically you're saying sum of the forces is equal to 0 because there's no mass. Excuse me. So 2TA basically is equal to 2TB. So there's a good relation. TA must be equal to TB, which reduces our unknown, and that will help us in a minute. But we still need one more relation. Remember, we had 4 unknowns. So far, we have 3 equations. This one, and this relation. The next relation is the relation between acceleration of A and B. So what we're going to do, and you've seen this in my other videos, hopefully you've seen this. I'm going to erase this, guys, for a second so I can show you the kinematics a little bit here. So maybe a little bit here. Okay, so look, I'm going to say, I want to establish a relation between A and B, acceleration of A and B. So I'm going to, from a non-moving reference, I'm going to call this position of A, and I'm going to call this position of C, pulley C, right? Let me go ahead and write the relation between A and C. Now, look, I could do it right here for you. I could say S sub A. What I'm trying to find is the total length of this rope. What rope I'm talking about? Let me use a different color. So I'm talking about this rope. Oops, going like this. So you see, what do I have? I have S sub A, right? Plus how many segments we have here? 2S sub C, right? Equal some, I'm going to call this rope, the length of it, L1. Now, what are we going to do with the other rope, which I'm going to call it L2? Let me change the color here. So you see there are 2 different ropes here. So we're talking about this rope now. If I could get the green going. So I had some problem with my pen here. One second, guys. If I could get this going. Just 1 second. Going to Sorry, guys, I had problem with my OneNote. So I drew the green rope here. So what I'm going to do now is I'm going to call this from a non-moving reference. I'm going to call this S sub D, and I'm going to call this S sub B, right? Keeping track of the position of these moving objects. Both B and D are moving. So now look what happens here, guys. The total length of this rope, this segment is S sub D, and this segment here is what? The difference between S sub D and S sub B. And I'm going to call that L2. All right. So what I'm going to do now, I'm going to take the derivative of these. So forgive me, guys, I got to erase some of these things so I can move up here and show you what's going on. So take the derivative of this, and what are you going to get? Remember, you're taking what? Time derivative of these, right? Time derivative of this basically says acceleration of twice. Sorry, if you take the time derivative twice, first you get the velocity, and then you get the acceleration. Acceleration of A plus 2 acceleration of C equals 0. This basically say acceleration of A is minus 2 acceleration of C. Remember, I need the relation between acceleration of A and B. All right, go ahead and do the time derivative of this guy twice. So first of all, you get 2 S sub D minus S sub B equal that L2, right? So we get 2 acceleration of D minus acceleration of B equals 0. So this says acceleration of B is equal to 2 minus 2 acceleration of D. All right, but this still doesn't establish a relation between acceleration of A and B. The last thing I got to do is establish a relation between acceleration of C and D. And that's easy. Look, guys, this is a constant length or distance. So can't I say that that constant, whatever that distance is S sub C plus S sub D plus some other constant here, which I don't care. So if you take the second derivative of this guy, finally you get what? Acceleration of C plus acceleration of D equals 0. Therefore, acceleration of C is equal to minus acceleration of D. And when you do this, acceleration of C and D, sorry, by the way, this guy is positive here, guys. So look, guys, if you replace acceleration of C by minus acceleration of D here, you get acceleration of A equal 2 acceleration of D, acceleration of B equal 2 acceleration of D. The conclusion is what? Here we go. That's the fourth equation. Acceleration of A must be equal to acceleration of B. Sorry for the mess, but I'm sure you can figure that out. Now look, guys, we have 1, 2, 3, 4 equations, so we are all set. So what I'm going to do, I'm going to actually rewrite this for you. TA plus 44 equal minus 3.1056 acceleration of A. Now remember, this one, TB and TA are the same, so I rewrite this TA minus 50 equal. And remember, acceleration of B and A are equal. So you see how we ended up having now a 2 by 2. Oops. I didn't clean this up for you. If you divide 50 by 32.2, let me see, what do I have here? I have a 1.553, roughly. Acceleration of A. Remember, acceleration of B and A are equal. So go ahead and solve these two equations any way you like. It's that simple. You just multiply this by negative and then you add the two. We end up getting acceleration of A. The interesting thing is that acceleration of A comes out to be minus 1.288 feet per second squared. Why negative? Negative implies deceleration, guys. And that's the way it should be, because remember, the problem says find the distance it travels before it comes to rest. Remember, it was moving at 5 feet per second, if you remember the beginning of the problem, going this way. You want to find the distance A travels before it comes to what? Rest. Final velocity of A is going to be 0. This is the initial. This is the final. Okay? So since this is a constant acceleration problem, one of the easier equations, remember, A, acceleration of A is constant. V squared minus V0 squared. Remember, this is V0 in a way, and this is the final velocity, initial final, equal to A S minus S0. So S0, we say 0 when the speed was 5 feet per second. This is our SA, and this is the acceleration of A. So final velocity 0, initial velocity 5. Acceleration, remember, is negative 1.288, which implies deceleration, and then times SA. So we go ahead and solve for SA. which happens to be about 9.7 feet, guys. All right, guys, sorry for, having some technical issue with the one, OneNote, and it happens once in a while. So I had to pause the recording and then come back, and then my pen wasn't working, and then things got messy. So I'm sure you can go back and forth and, stop the recording, or stop the video. It's going to be posted soon to YouTube. All right, as always, thank you for watching and listening. Please subscribe if you like the video and like the video, and I'll have more examples for you and more problems on different topics. Again, as always, thank you very much, and I'll see you soon.